Right, so can you guys see my screen now?
Yes, sir.
All right, so our topic is problem solving. Okay, so it is actually composed of mainly three topics. Okay, so two type of reasoning and then a counterexample. Okay, so the first one is inductive reasoning. Okay, so once you've heard the word inductive reasoning, there's only one meaning or there's only one definition that should come up to your mind. That is, when you say inductive reasoning, you're basing the things or you're basing it on a raw data or a specific example. That is called inductive reasoning. Okay, so when you say inductive reasoning, you're basing your conclusion, you're basing your answer, you're basing your observation, or you're basing your conjecture, okay, on a specific example. Okay, so if there's a given example like three or more, then that is already inductive reasoning. But if you're basing your result or your conjecture or your observation based on a principle, based on a general conclusion, that is the other one, which is deductive reasoning. Okay, so for inductive reasoning, you're basing your conjecture or your conclusion on specific examples. Okay, so inductive reasoning is a process of reaching a general conclusion by examining specific examples. Okay, so when you examine a list of numbers and predict the next number in the list according to the sum pattern you have observed, you are using inductive reasoning. Okay, as long as you have a basis, okay, that is just actually a data or an example, that is already inductive reasoning. Okay, so let's have an example for you to be able to understand a little bit more. So use inductive reasoning to predict a number. So as you can see right here, we have two numbers wherein it is asking us to predict the next number in each of the following lists. So the first one is 3, 6, 9, 12, 15. So what could be the next one? What is the next one, guys? What is the next number?
18, sir.
18. So I think all of you will answer 18. So how did you guys come up with that 18? You base it from the
Sir,
past examples or from the past patterns. Okay. So imagine without pattern, will you be able to say that, okay, so the next on 15 is 18? Okay. Say, of course, you need enough examples for you to be able to say that, all right, so the next number is 18. But if you only have 15 and then it is asking you what is the next number, then probably the one that you're going to answer is 16 or 15.1. So there's a lot of, next number to it. But in here, we proved that, it's incrementing the by 3. So you could say that the next number is 18. So in that way, you've used your inductive reasoning to predict the next number, which is 18. Okay. How about the second one? 1, 3, 6, 10, 15.
21, sir.
21. So again, I'll repeat. So what about if there is no 1, 3, 6, 10? There's only one number, which is 15. Okay. So again, you might say that the next one is 16 or 15.1. So in inductive reasoning, you need at least 3. Okay. 3 or more. But if there's no other examples, and then you conclude that the next number is 16 or 18 or 21, then you've used deductive reasoning. All right. So if there's not enough examples, meaning you've already dive into the conclusion without even looking back at the past examples, meaning that's deductive reasoning. You've used a certain principle. You have a basis, okay, wherein they have already proven very long time ago, like mathematicians, they proved that this one is the equal to this one, even though they are not the same. It's just different uh, uh, this one derivation. Okay, like for example, the differential and integral. So differential, we can convert it to this. Integral, you can convert it to this, and so on and so forth. Okay, so for the number 2, the answer is 21. So as you can see, we've started from plus 2 are difference of 2, and then a difference of 3, difference of 4, difference of 5, and then of course the next one is difference of 6. So 15 plus 6 is 21. Okay, so we base it from those 5 examples or those patterns. Okay, so here are the solutions. So I will leave the reading part on you guys. Okay, so since we already answered that, the next one is 18, the next one is 21. And if you still didn't understand how did we get 18 and then 21, so just read back on this one. So as usual, after having that example, you're going to have a quiz, which is very similar with the example, of course. So use inductive reasoning to predict the next number in each of the following lists. So actually, this one is already a bonus since you have already uh you already know this one. Okay, we've discussed this many times in the past few meetings. Okay, predicting the next number. So number one and number two only. Okay. So another example when it comes to applying, okay, inductive reasoning is to make a conjecture. Okay, so making a conjecture is like making your thoughts or your final conclusion, your final uh, realization. Okay, so let's say we have here a procedure. So what's here the following procedure? Pick a number, multiply the number by 8, add 6 to the product, and then divide the sum by 2, and then subtract 3. Okay. So complete the above procedure for several different numbers. Use inductive reasoning to make a conjecture about the relationship between the size of the resulting number and the size of the original number. So it is asking you to make a conjecture between the relationship between the original number and then the result number after doing those procedures. So in here, after getting the correct answer, after getting the final answer, so you must make your final conclusion like, I realized that the original number is times 5 of the result, something like that, or the original number is just the same with the result. Okay, even though it's it has many procedures, but of course that's quite impossible. Anyway, so we'll see what will be our conjecture later on after doing those 5 steps or 5 procedures. So the first one is, of course, picking an original number. So let's say, just for us to have a common result, suppose we pick 5 as our original number, then a procedure would produce the following results. So just put here your original number. Then the second procedure is multiply it by 8. So 5 times 8 is 40. And then add 6. So 40 plus 6 is 46. And then divide it by 2. So 46 divided by 2 is 23. So, and then the last one is subtract it by 3. So 23 minus 3 is 20. So as you can see right here, our original number is 5, and then the uh, result or resulting number is 20. So from here, we could say that, started with 5 and followed the procedure to produce 20. And then if you, let's say, of course you haven't realized it yet with having one result only, so maybe you want to try another number instead of just 5. So let's say you've started with 6. So if you do those steps, okay, and then you have 6 as your original number, it will produce or it will give you a result of 24. Okay, so 5 to 20, 6 to 24, and then if you have 10, say you want to try another one, okay, which is starting with original number of 10. So from original number of 10 to 40. So from here, you might be able to have your conjecture already. Okay, so from 5 to 20, 6 to 24, and then 10 to 40. So from those past 3 results, okay, you might have already your conjecture. So you could say that 20 and then 5. So it's like, dividing it by 4 or multiplying it by 4. So we could say that, okay, so maybe times 4 of the original number. Let's see the second one. What about the second one? So 6 and then 24. Oh, which is also the same. So dividing it by 4 will give you 6, and then multiplying it by 4 will give you 24. So, just to verify to check whether your conjecture is correct or no, You've tried another one, which is a 10. So 10, and then the result is 40. So from here, you might have already proven that your conjecture is correct, wherein the original number is times 4 of the result, okay, from 10 to 40. So multiplying it by 4 will give you 40, and then dividing it by 4 will give you 10. Okay, so in each case of these cases, the resulting number is 4 times the original number. So we conjecture that the following given procedure produces a number that is 4 times the original number. So that is how you conject, or that's how you, you know, uh, come up with the final conclusion or final thoughts. Like, putting any number in here, say any number, let's say 100, 1,000, 1,000,000, or any na 500, it will be always times 4, okay, of the result from the original number. So did you guys get it so far on how to make a conjecture?
Yes, sir.
All right, so before you're only getting the next number, so no, yeah, you can still have your conjecture here, like it's incrementing by, where's that one? It's incrementing by 3, and then it's incrementing by 1 starting from 2, okay? But in here, you can come up with a uh, fixed thought or final thought, okay? Having a different numbers, because in here it's uh, already fixed that the result is 21. Okay, you cannot come up. What about if the number is 2? You cannot say that here. So in here, you can do that here because it gives you the privilege to pick a number. Okay, so the same with other equation, of course, or other formulas. You're just changing the result, but of course with the same way of solving it. Okay, so after this solution, of course, you're going to have a quiz. So the same process. Okay, you have 5 procedures, I guess. 1, 2, 3, 4, 5. Yeah, 5 procedures. And then, just complete the above procedure for several different numbers, and then use inductive reasoning to make a conjecture about the relationship between the size of the resulting number and the original number. So the same. So you can start actually in any number. This is just a base. This is just in case. Okay. So yeah, the same question. So it is asking uh, the relationship between your original number and then the resulting number. Okay. So yeah, just look on this one on the canvas. So anyway, this is multiple choice. So there's a lot of choices. So just do those 5 process, and then you'll be able to answer it right away. All right. So another one is with the use of period of pendulum. Okay, so long, long time ago, Galileo Galilei used inductive reasoning to discover that the time required for a pendulum to complete one swing, called the period of pendulum, depends on the length of the pendulum. Okay. So he realized that before, the longer the length of the pendulum, the more swings that it can do. So of course, before, Galileo did not have a clock. Okay, so he measured the periods of pendulum in heartbeats. So the following table shows some results obtained for pendulums of various lengths. So for the sake of convenience, a length of 10 inches has been designated as 1 unit. So as you can see right here, he've come up with another basis wherein he's using his own heartbeat. Okay. So in here, you could say that if he has a 1 unit wherein it's 10 inches, okay, just multiply this one by 10. So 1 unit is equivalent to 1 period of pendulum, wherein that period of pendulum is the same with his heartbeat. So take note, it is his heartbeat. It is Galileo Galilei heartbeat. Because of course, all of us doesn't have the same heart rate or heartbeats. So Some has a very fast heartbeat, some has a very slow heartbeat, and most of us are maybe normal. But for Galilei, with 10 inches of length of pendulum, can do one period of pendulum or one swing. So when we say one swing or one period of pendulum, okay, it is the time it takes for pendulum to swing from left to right and back to its original position. Okay, so from here, so it should go back to its original position for us to be able to say that it's one swing already or one period of pendulum. Okay, so we have your graph wherein he come up with those results. So one length is one, four lengths is two heartbeats or two period of pendulum, 9 is to 3, 16 is to 4, and then 25 is to 5, and then 36 is to 6. So again, which is kind of similar with the past examples. So